Hello, ladies and gentlemen. Welcome back. We are on chapter 9.3. This is part 1. But before we begin, let me pull in Schoology really quick. All right, just a reminder that above the video, I do have links to some of the notes if you want to print those off. Okay, so I've got them in order. And then the formula chart, which you should already have, and then the flow chart for chapter 9, which I'm going to talk about in a little bit. And just a reminder that there are other videos from the College Board. We're really getting into the heart of what we want to accomplish in this class with being able to do some hypothesis testing, and you'll see when we get to the end on inference what we're driving towards. So again, please watch these videos, highly recommended. These are pretty short compared to mine, okay, but I would really advise watching them. I know you guys are probably really tired of watching videos by now, but unfortunately, that's the way we have to do things at the moment. All right, so let me move this out of the way for now, and let's get started. Now, before we get into chapter 9.3, I do want to do like a warm-up with what we did in the last one. So let me get to the right page. First of all, there we go. So suppose that 47% of all adult women think they do not get enough time for themselves. Now that's a proportion, okay? Don't get proportions mixed up with the new lesson today, which is means. An opinion poll interviews 1,025 randomly chosen women and records the sample proportion who feel they don't get enough time for themselves. Describe the sampling distribution. Okay, now let's look at the other questions before we continue. Then B, the truth about the population is that the proportion is 0.47. In what range will the middle 95% of all sample results fall? Okay, that's going to get into that 95. Remember the 68, 95, 99.7 rule, the empirical rule? And then what is the probability that the poll gets a sample in which fewer than 45% say they do not get enough time for themselves? Show your method. All right, so let's go back to C. Now, I've already got these typed out. So again, use your power of pause and rewind if you need to, if I'm going too fast. So here again, here's our situation. Describe the sampling proportion p hat. Okay, there is actually quite a bit to this. Here we go. So we're going to let p hat equal the proportion of women who think they do not get enough time for themselves in a random sample of n equals 1,025 adult women. Okay. The mean mu sub p hat, look at the notation folks, equals 0.47. Now, the rule of thumbs. We got to memorize these. Remember, those rule of thumbs are on that chart that you have access to. You can print it. Okay, so here is again the standard statistic, but if we go down, all right, for proportions, here's rule of thumb number 1. Okay, if the population is greater than 10 times the sample size, then we can use the square root of all of this for the standard deviation. Rule of thumb number 2, if the sample size times the proportion is bigger than 10 and the sample size times its complement is greater than or equal to 10, then we can use the test statistic, the standardized test statistic. Okay, that tells us it's a go. You can go ahead and use it. All right, let me get back to here. Whoops, wrong one. Let me get to the right one. There we go. So I've got everything printed out here. So again, use the power of pause if you need to. The population is clearly at least 10 times as large as the sample. So rule of thumb number 1, okay, that's just intuitive, folks. Think about this. It's talking about, okay, it's talking about all adult women. Okay, well, there's definitely more than 10 times the sample size. 10 times 1,025 is what? 10,025? There's definitely more adult women than 10,025, right? So just think intuitively there, all right? So Rule of thumb number 1 says that, yes, we can do the standard deviation. So we took the square root of p hat, or p, not p hat, p times its complement and divided it by the sample size. So we get a standard deviation for this situation of 0.0156. Okay, remember it's p, not p hat when we do standard deviation. Very important detail. Rule of thumb number 2, the two conditions, n times p and the complement times p. Notice this one's 481.75. That's bigger than 10. And this one's 543.25. That's bigger than 10. They are both satisfied. So that means that we can use the distribution of p hat. It's approximately normal. That means we can use the z-score. Okay, we can use the test statistic. All right, so that was all for part A. Part B. All right, so in what range will the middle 95% of all sample results fall? Okay, well, folks, draw your picture. You put your mean right here, right? Here's your mean, 0.47. And we found the standard deviation of p hat right here, 0.0156. Okay, let me write that on here. So the standard deviation of p hat is 0.0156. So remember how that works, folks. Okay, so as you're going up, you add one standard deviation and then you add two standard deviations. So the 0.5012, that's two standard deviations above the mean. And then you subtract the 0.0156 going the other direction. Okay, this is all from chapter 2. And you end up 2 below at 0.4388. Okay, because remember, 95% is 2 below to 2 above. So the middle 95% of all sample results will fall within two standard deviations of 0.47 or in the interval 0.4388 to 0.5012. Okay, this is a foreshadowing of something we're going to do with confidence intervals in the future. All right, so 95% are going to fall within this interval. Okay, all right, part C. What is the probability that the poll gets a sample in which fewer than 45% say they do not get enough time for themselves? Show your method. All right, well, we already investigated that we can use the z-score, the test statistic. So I set it up. Okay, what's the probability that p hat is less than 0.45? Okay, I found the z-score. Now, I didn't show that, but I guess I probably should show that. So the z equals, okay, the 0.45 minus the 0.47, right, because that's p, divided by the standard deviation, which we found to be 0.0156. Okay, if we do that, ladies and gentlemen, we get negative 1.28. Okay, that's our z-score right here. So I drew a picture. And then, remember, we can use our calculator. Let me just run through that again really quick. So we can use, so if you use the z-table, you're going to get 0.1003. If you use your calculator, let me pull the calculator over as soon as I can find it. There it is. All right, let me get out of this window. Okay, we can go to the normal CDF, remember, second vars, number 2. Now, since it's shaded to the left, I'm going to pick a really small lower value. I'm just going to say negative 100. And then my z-score of negative 1.28, that is my upper bound. And I'm going to paste that in, and voila, I get 0.1003. All right. Actually, I've got that backwards. That's amazing. I've got these backwards, folks. Okay, so with the calculator, you get 0.1003. And I believe with the table, you get the 0.0998. Okay, so sorry about that, folks. And then our conclusion, ladies and gentlemen, okay, anytime we do this, we have to type a conclusion. Okay, you have to do that here. You can't just find that probability, you then have to give your conclusion. So the probability that the poll gets a sample in which fewer than 45% say they do not get enough time for themselves is about, okay, depending upon which one you use. So if you use the other one, you could have the 0.1003 here, okay, or 10.03%. All right, that was just a quick review, even though that took 11 minutes, of what we did in our last lesson. All right, let's get rolling here. So I want to quickly revisit that virtual lab applet. Okay, so again, we looked at this, and remember what happens here. So right now, my sample size is 5. So again, I would pick 5. I would find the mean of those 5, and I would drop that into the next curve. Okay, and then I'd pick 5 more. It's going to be a different mean, and so on. Okay, and if I do 10,000 samples of a sample size of 5, it looks like that. All right, now remember what happens here. If I change my sample size, okay, how large my sample is. Okay, here I'm going to pick 25 of them and then find the mean of those 25 and drop it in, and so on. And if I do 10,000 of them, look at how small, look at how narrow that is. Okay, the variability is really small. That is one of the most important things to understand in AP statistics, how the sample size affects your variability. That, ladies and gentlemen, is called the central limit theorem, and you better not forget what it means. The central limit theorem discusses the shape and only the shape of the sampling distribution of the mean. Now, this is for means, not proportions. Means, okay? With n is sufficiently large. If n is not large, the shape of the sampling distribution more closely resembles the shape of the original population. Thus, there are 3 situations to consider when discussing the shape of the sampling distribution. Okay, please write these down and get to know them well. All right, again, use the power of pause and rewind. 1, the population has a normal distribution. If the population has a normal distribution shape of the sampling distribution, it'll be normal regardless of the sample size. Okay. Right now, this population, this black normal curve up here, that's our population distribution. That is saying, okay, it's normal, right? It's normal. And what that is saying is that no matter, okay, right now I got a sample size of 2. No matter the sample size, okay, when I do sampling distributions, I pull samples from the population, it will also be normal. That's a really important fact to remember. If the population is normal, no matter what the size is of your sample, your sampling distribution will also be normal. All right? 2, any population shape, small n, of sampling distribution is similar to the shape of the parent population. Okay, that's kind of hard for me to show you with this sampling distribution. So let me do that. Let me just do something like, let's say our sample or our population is skewed to the right. Okay, it is skewed to the right. So if I keep my sample size 2, okay, well, no, let me increase my sample size to 5. Okay, so I would do 5, you know, it would drop it in, and so on. Okay, let me do 5 at a time. 5 more, 5 more, 5 more, 5 more, 5 more, and so on, doing sample sizes of 5. I'm just doing a whole bunch of them. Okay, again, it's really kind of hard to show you on this applet, but okay, here's 10,000. Ooh, look, it kind of worked. Notice it's kind of skewed to the right. Okay, it's so that's what B is saying. Okay, that's what B is saying here. That any population shape, small sample size, the sampling distribution is similar to the parent population. Okay, so you can kind of see it in this display. Okay, it's the parent population is skewed to the right, and you can see that this is kind of skewed to the right. Okay, so remember that. 3, any population shape, large N, meaning a large sample of the sampling distribution is close to normal. So as long as your sample size is large, it doesn't matter what the population looks like. Okay, if I make my sample size 25 and I do 10,000, I don't see anything skewed in that at all. Okay, let me do another weird one up here. Okay, let me do a population. I don't know what this would be for, but let's say we had a population distribution that looked like this. Okay, whoa, that is definitely not normal, right? But if I keep my sample size 25, I keep my sample size large, guess what? I sampled and I'm still going to get a normal distribution. That's what that central limit theorem is saying. All right? Okay. So on page 598, you will find this. Draw a simple random sample of size n from any population whatsoever, okay, with mean mu and finite standard deviation. When n is large, the sampling distribution of the sample mean x bar is close to the normal distribution. Notice, ladies and gentlemen, we've got a slight change in our standard deviation. We are now going to take the standard deviation and divide it by the square root of our sample that we took, our sample size. Okay? 593. Mean and standard deviation of the sample mean. Suppose that x bar is the mean of an SRS of size n. All right, so that's what this is. So first of all, the mean of x bar equals the true mean. The standard deviation is the standard deviation divided by the square root of n. All right, see formula sheet. All right, let's look at the formula sheet, ladies and gentlemen. So if we go to the last page, again, here's our test statistic, here's our z-score. All right, here is, ladies and gentlemen, here is our standard deviation. So our z-score now is going to look like this. It's still going to be x bar minus the mean, but now we're going to divide by the standard deviation divided by the square root of n. And as n gets larger, as n gets larger, the variability is going to shrink. All right. Now, I also have that printed out for you, ladies and gentlemen, on this extra sheet. Right here, talks about 9.3. All right, right here it's talking about the mean. Here it's talking about the standard deviation. So if you want to just print this out instead of writing it all down. And then here's what our z-score now looks like. Okay, and then the population needs to be at least 10 times as large as the sample. Okay, but we don't call this one a rule of thumb. Rule of thumbs are only for the proportions. All right, details, details, details. And then right here is what I just talked about. So read through that and know that really well, please. Also, I have attached a flow chart, okay, for chapter 9.3. So whenever you read a problem, you got to decide, is it a proportion? Is it a mean? Well, if it's a proportion, then you're going to follow this side. Okay, and then you got to go through your rule of thumbs to see if you can do your test statistic. Okay, if it's a mean, then you're still going to look for the population needs to be at least 10 times as large. That means we can use this as our standard deviation, and we can do, according to the central limit theorem, as long as the sample size is large enough, we can then do our test statistic. All right. All right, so there's that for you. Okay, let's keep rolling here. So, ladies and gentlemen, page 593, again, this goes through what's on that other printed sheet. The behavior of X bar in repeated samples is much like that of the sample proportion P. And I already went through these. Okay, I'm not going to read these to you. I'll just slowly scroll. So if you want to write these down or just print them on that other sheet, go ahead. Oh, one thing I do want to point out in red right here. The value of X bar has less spread out for large samples. Their standard deviation decreases at the rate of the square root of n. So, okay, here's a really important fact to remember. You must take a sample 4 times as large to cut the standard deviation in half. So if I have a standard deviation of 4, to cut that and my sample size is 10, okay, to cut that standard deviation in half, folks, if I want a standard deviation of 2, I need to take a sample 4 times as large. So that means I would need to have a sample of 40. Okay, a really important fact to remember. If you want to cut a standard deviation in half, you need to take 4 times as large a sample, okay, because the square root of n, think about it. All right, okay, so that leads to what we're going to get into from here on out. Sampling distributions are the key to understanding statistical inference. With an understanding of random variables and sampling distributions under our belt, we are now ready to begin the study of inference. Okay, not quite done yet because I want to go through an example and then I'm going to do more in another video for part 2. All right, so here we go, ladies and gentlemen. Let us look at this question. Now I've already got the answer to it, but let's look through this one. Okay, again, you can print this sheet if you want to, right above the video. In response to the increasing weight of airline passengers, the Federal Aviation Administration, the FAA, in 2003 told airlines to assume that passengers averaged 190 pounds in the summer, including clothes and carry-on baggage. But passengers vary, and the FAA did not specify a standard deviation. A reasonable standard deviation is 35 pounds. Weights are not normally distributed, especially when the population includes both men and women, but they are not very non-normal. A commuter plane carries 20 passengers. Can you calculate the probability that a randomly selected passenger weighs more than 200 pounds? If so, do it. If not, explain why. Well, in this situation, no, you cannot do it. Why? If we are randomly picking from that sample of 20, okay, we can't calculate the probability of a randomly selected passenger. We do not know the distribution of weights. 20 is a very small sample. In other words, we don't know the individual weights of each passenger. Okay, so that's not going to work in that scenario. All right. Next question. Can you calculate the probability? Whoops, let me move that too far. Can you calculate the probability that the total weight of the passengers in a flight exceeds 4,000 pounds? If so, do it. If not, explain why not. Well, guess what? Here we can, ladies and gentlemen. We can do that. So the first thing we're going to need to do, ladies and gentlemen, is we are going to need to let me get my pen rolling here. We're going to let X bar equal W divided by 20. Okay, well, the W is the total weight, which here is the 4,000. So we're going to take the 4,000 and divide it by the 20. So we're going to say X bar is 200 pounds. Okay? Now, I'm going to type this part instead of writing it. So since the sample size is large, okay, our sample size is large. In the situation A, it was only the 20 passengers, right? So think about that. So n equals 20. Okay, that is actually a large sample size. The sample distribution is approximately, don't ever say it's normal, approximately normal. All right, let me continue with the pen. Now, with X bar, whoops, let me back that up, with the mean X bar equaling 190 pounds. Okay, that's what's given in the problem. Okay, right here. So our mean X bar is 190 pounds. And, okay, now the standard deviation, ladies and gentlemen, the standard deviation is going to be 30, whoops, not X, yeah, X bar, is going to be 35. Okay, where did that come from? That comes from right here, ladies and gentlemen. But we're going to divide that by our sample size, the square root of our sample size, which is 20. And if we do that calculation, ladies and gentlemen, we're going to get 7.826 pounds. Okay, so that's our standard deviation. All right, so we want to know what is the probability that W is greater than 4,000 pounds. Okay, well, now we're going to go ahead and we're going to switch that to X bar is 200, greater than 200 pounds. Okay, that's what we did in green right up here. Okay, so because we switched it to an individual passenger. Okay, we have to switch it to an individual passenger. So greater than that passenger is greater than 200 pounds. Okay, now if I do my Z statistic, ladies and gentlemen, I'm going to go ahead and take my 200 minus the 190 and divide it by the 7.826, which is the standard deviation that we found up there. And we're going to get a Z-score of 1.28. So now I'm going to write the probability that Z is greater than 1.28. All right, now if I look at a picture, always a good idea to draw a picture, folks. 1.28, it's going to be greater than that. Okay, and if we do that, ladies and gentlemen, let's see. I think we already kind of know the answer to that because it's going to be just like this one, isn't it? Okay, except it's going to be on the other side. It's just like the warm-up we did today. All right, so now my lower bound is the 1.28, and my upper bound, I'm going to just make that a large number, 100. And then I'm going to go ahead and paste it in and calculate. And I'm going to get 0.1003. All right, so I get 0.1003. So this is where we need to type a conclusion, folks, or write a conclusion. Okay, you can't just stop there for these types of problems. You do have to go one step further because I'm getting you ready for that inference stuff, and you always need to type something out. So we're going to say that there is about a 10%, you can change it to a percent if you want, there's about a 10% chance that the total weight exceeds the limit of 4,000 pounds. Now that's not the only way you could write that. You could write that as long as you get that message across. Okay? All right. Let's keep rolling here. Okay, that's it on that page. Again, rewind, watch if you need to rewatch that. All right, the next part. The score of students on the ACT college entrance exam in a recent year had the normal distribution of mean of 20.4 and a standard deviation of 5.8. What is the probability that a randomly chosen student scored 24 or higher on the ACT? Okay, we're not going to go through all of the conditions here. We're just going to jump right in and find the probability of this. So we're going to go ahead and we're going to write the probability of X. Now, we didn't define it, but X would be this individual student score, right? We want to know what's the probability that it's going to be greater than or equal to 24. Okay, again, the equal to part really doesn't matter, but it says 24 or higher, so we will put that equal to in there. All right, so that's going to equal. Now I'm going to change that to a z-score. Okay, so I'm going to need to do some scratch work off to the side, and please always show your scratch work. So we're going to take 24 minus the mean, 20.4, and we're going to divide it by the standard deviation. Now, ladies and gentlemen, this is one student. So I'm going to show you that I could put the square root of 1 underneath because the sample size is a single student. Okay, but obviously the square root of 1 is 1, and when you divide by 1, it doesn't change it. So in this situation, having that square root of 1 underneath doesn't matter. Okay, and what we're going to end up with here, ladies and gentlemen, is a z-score. Okay, I didn't leave myself enough room, so I'm just going to write it over here. So the z-score that we end up with here is 0.62. Okay, 0.62 equals. Now again, I can use my calculator. So my upper bound is going to be the 0.62. And lower bound, sorry about that. Lower bound is 0.62, upper bound is 100, and I'm just going to go ahead and find that probability, and I get 0.268. All right, so if I would type a conclusion here, I'm not going to, we would say that the probability of a randomly chosen student scoring 24 or higher is about 26.8% if we changed it to a percent. Okay, part B, what is the mean and standard deviation if it's 30 students? Whoa, okay. So, what is the mean? All right, well, it's not asking us to find the probability here. So we say the mean, ladies and gentlemen, the mean of X bar is still going to be the true mean, which it told us is 20.4. Okay, the standard deviation of that mean is going to be the 5.8 divided by the square root of 30. So that's going to make that standard deviation way smaller. See how that's going to make the variability shrink? And what we're going to end up with there, ladies and gentlemen, is, let's see, I got to actually type this in. So if we take 5.8 and divide it by the square root of 30, yep, we get 1.0589. All right, 1.0589. Generally, 4 digits is good on the standard deviation. Okay, so now the question is, well, what is the probability of those 30 students having a 24 or higher? So again, the probability of X, again, I didn't define X, but X would be a score of 24 or higher, equals the probability of the z-score being greater than or equal to what? Okay, well, the z-score now, I'm going to go ahead and take my 24 minus the 20.4 divided by the standard deviation that I got in part B. And when I do that, ladies and gentlemen, I'm going to get a z-score of 3.4. That is a very high z-score. Okay, a z-score that high, ladies and gentlemen, is going to give, most likely the calculator is going to give it to you in scientific notation. So if I do 3.4, think about it, our normal curve, we only go out 3 standard deviations. So when we see this, ladies and gentlemen, I want you to think about this. See that E with a -4? So that means 0.0003, okay? 0.0003. So basically, ladies and gentlemen, there's a 0% chance of this happening. Randomly selecting 30 students that have a 24 or higher based on this information, chances are that's not going to happen. But think about this. If it does happen, then the mean must not be 24. Okay? It must be something else. Keep that in mind. Okay, this is telling us that that should not happen. But if it does happen, that means the mean is probably not 24. That's getting into our inference later on. All right, let me see if I can wrap this up here. We're getting on 40 minutes. All right, would your answer to part 1, 2, or 3 be affected if the distribution of ACT scores in the population was distinctly non-normal? Well, yes. In the first sample, okay, let me make this a little bit smaller here. In the first sample, it was only one person. So the answer to problem 1 would be affected because the sample size is only one student. Okay, so yes, it would affect that. Okay, for problems 2 and 3, the sample size of 30 is large enough that the central limit theorem tells us that it will, well, that X, I'm going to do this, that X bar will be approximately normal. Okay, let me make that a little bit smaller here so it fits in the space. Excuse me. All right. Now, one thing I want to say right now, do not use the words central limit theorem on the AP test. They just would like you to say that the sample size is sufficiently large, okay? A few years back, they decided they didn't like students just using the central limit theorem. They would rather have students say that the sample size is sufficiently large. So now, ladies and gentlemen, I'm going to do a little notation here. So remember, capital N stands for approximately normal. And then the first number is our mean, 20.4. And then the standard deviation for the sample size of 30 is 1.0589. All right, so there's the notation for that. All right, let's keep rolling here. All right, if you need to pause and take a break, folks, pause and take a break and then come back. All right, Judy's doctor is concerned that she may suffer from hypokalemia, okay? Low potassium in the blood. There is a variation both in actual potassium level and in the blood test that measures the level. Judy's measured potassium level varies according to the normal distribution. There's the mean, 3.8, with a standard deviation of 0.2. A patient is classified as hypokalemic if the potassium level is below 3.3. If a single potassium measurement is made, what is the probability that Judy is diagnosed as hypokalemic? All right, so again, P would be, or X would be less than is the amount, right? So in this case, to be hypokalemic, it would need to be, you know what, I'm going to change this, ladies and gentlemen, to, do I want to change it? Yeah, I'm going to change that 3.3 to 3.5, okay? We're going to change that to 3.5. So then I'm going to go ahead and I'm going to put 3.5 here. So she's hypokalemic if her blood level is below 3.5. Okay, now I'm going to go ahead and find that z-score. All right, so over here I'm going to go z equals, I'm going to go ahead and take the 3.5 minus the 3.8 and divide it by the 0.2. Now, I could put the square root of 1 underneath, but again, it's only a single measurement, so that's not necessary. And we get a z-score of negative 1.5. Okay, put that into the calculator, and we're going to get 0.0668. So the probability that she is diagnosed as hypokalemic is almost 7%. If measurements are made instead on 4 separate days and the mean result is compared with the criterion 3.5, what is the probability that Judy is diagnosed with as hypokalemic? Okay, so 4 measurements. So again, it's still going to be the probability that X is less than the 3.5. Okay, but my z-score is going to change here, ladies and gentlemen, because we now have a sample size of 4. So that means now I have the 3.5 minus the 3.8. We divide it by the 0.2, but now that's being divided by the square root of 4. Now, I would do these calculations separately. Okay, so on top, we're going to have negative 0.3, and then on the bottom, okay, don't try to type it in all at once. That's where mistakes are generally made. So on the bottom, we're going to get 0.1. And so then we're going to end up with a 3 for our z-score. Well, again, ladies and gentlemen, that's a very high z-score. Okay, and that high z-score, again, if you type that into the calculator, okay, you're going to put in a 3. It's going to be, oh, it's negative 3, folks. My apologies. Almost goofed there. I was like, wait a minute, it can't be 3. It's negative 3, folks. So the z-score is negative 3. We're going to get, oh wait, I still did it wrong. Okay, that's the upper bound. Okay, wow, I'm really messing up here. Okay, my lower bound is negative 100. Sorry, folks. And my upper bound is the negative 3. Woo! Okay, think about that. Okay, my upper bound is the negative 3. So there we go. All right, here we go. There we go. That's better. 0.0013. Okay, so 0.0013. And let me make that negative because I goofed. This is a negative z-score. Silly Mr. Ellering. All right, so basically, ladies and gentlemen, with 4 samples, the probability of her being diagnosed as hypokalemic is basically 0%, less than 1%. But if it does happen, that might mean that her reading of 3.5 is not accurate. Okay, lots to think about. All right, I believe that's it for this. Let me double check. Let me go a little bit lower. All right, good. Okay, because we're up to 45 minutes and that's enough for today. I will try to keep the next video short. Again, AP stats, I apologize, I really can't make these any shorter. All right, see you in class soon.